In this video, we are going to talk about percent composition and then how we can use the percent composition to calculate the empirical formula for a compound. Now, I can determine the percentage of the total mass that each element contributes to the mass of the compound from the molecular formula. If you think about it, I have a compound, and that compound is made up of its specific elements, maybe 2 elements, maybe 3, but it's made up of several elements. Its total mass is calculated by adding the masses of each element and how much they contribute. To calculate mass percentages of each element, then all I have to do is take the mass that comes from one element divided by the total mass of the compound times 100. And I can do that for however many elements I have. We call this mass percent composition or percent composition. And we can do it for one element, for all elements in one compound. It doesn't matter. But we can do it for each element as well as singly. Here is the formula that we're going to use. The percent by mass of a specific element in a compound is equal to N times the molar mass of an element divided by the molar mass of the compound times 100. N in this formula is the number of moles of an element that is contained in 1 mole of the compound. For example, if I have 1 mole of water, the formula is H2O. 1 mole of water contains 2 moles of hydrogen and 1 mole of oxygen. So for hydrogen, this N will be 2 times hydrogen's molar mass divided by the molar mass of water times 100. For oxygen, it will be 1 because I only have 1 mole of oxygen for every mole of water times the molar mass of oxygen divided by the molar mass of the compound times 100. Let's take a look at an example. We're looking at hydrogen peroxide with the formula H2O2. The first thing that we need to do when we're doing percent composition problems is figuring out the molar mass of my compound. We should be familiar with this by now because we've been doing it for a little bit of time, but we figure out how many moles of each element we have. We have 2 moles of hydrogen. So to figure out the mass that comes from the hydrogen, I take however many moles I have, so 2 multiplied by the molar mass of hydrogen, which is found underneath it in the periodic table. So 2 times 1.008 grams, plus, then I move to the contribution that the oxygen is giving to the mass of the compound. I have 2 moles of oxygen, so I have to multiply the molar mass of oxygen by 2. So plus 2 times 16 grams. And if you do the math, you should get 34.016 grams. That is how much 1 mole of hydrogen peroxide weighs. When I go to do the mass percent composition of hydrogen and oxygen, these are done similarly. I have 2 moles of hydrogen, so my N equals 2. If you remember in the previous slide, the formula, 2 moles multiplied by the molar mass of hydrogen, which is 1.008 grams, over the mass of 1 mole of compound, which I just calculated up here, 34.016 grams. It's multiplied by 100 because it's a percent. Then, if you think in terms of mass, basically mass of one component divided by the total mass times 100, that's the percent by mass of this element. And then we do the same for the next element. The mass percent for hydrogen then comes out to be 5.927%. We can do the same thing for oxygen. So I have 2 moles of oxygen. Each of them weigh 16 grams. So multiply 2 by 16 gives me 32, divided by the total mass, which I calculated to be 34.016, multiplied by 100, giving me 94.073. Now, in this compound, because there's only two elements, once I calculate one, I can always just take 100% and subtract the percentage of one of the elements to get the percent of the other, because the sum of the percentages of the individual oxygen and hydrogen here has to equal 100%. I cannot have any more or less than 100%. They make a whole, right? The sum of these two equals the total, and the total is 100%. It's 99.997, which rounds to 100%, and that's what I have to be within. So I could have also calculated the oxygen percentage by taking 100% minus the percentage of the hydrogen to give me the oxygen. Here's a sample problem for you to try. Lithium carbonate was the first mood-stabilizing drug approved by FDA for the treatment of mania and manic depressive illness, also known bipolar disorder. Calculate the percent composition by mass of lithium in lithium carbonate. Now, I could have made you calculate lithium, carbon, and oxygen, but I am only looking for the lithium. You could, if you want to get more practice, you can do the carbon and the oxygen and then check your math, add the percentages all three and see if you get 100%. That would be a good thing for you to practice. But for this problem, I'm only asking that you calculate the mass percent of lithium. So you figure out the total mass of lithium carbonate by adding all its components multiplied by how many moles of each you have. Then you figure out what the mass of lithium is alone, divide that by the molar mass of lithium carbonate times 100 should give you the mass percent of lithium. The next bit that we're going to talk about is how to take the mass percent composition and to determine the empirical formula of a compound. So let's look at a couple of examples because it will make more sense to talk about this concept while we're actually doing a problem. In this case, we're sort of working a little bit backwards. Let's say we have a compound with the mass percent composition of 92.26% carbon and 7.743 hydrogen. Now, the percent composition is the same. It doesn't matter how much of the compound we have. We can have 10 grams of the compound. We can have 100 grams, a billion grams. It doesn't matter. The percent composition will not change because that is how we get compounds. Those elements combine in specific ratios to give us the formula of a compound. And it doesn't matter how much of the compound I have in mass, that is, it will always be, so the mass percent composition will always be the same. So to do these problems and keep the math very simple, we can assume that we have exactly 100 grams of the compound. And you'll see why that is easy. But in these types of problems, I encourage you to just get in the habit of assuming, unless it is specifically given to you, just assume 100 grams of the compound because it is easy for the math. Now, from the percent composition of each element, we can back calculate the mass of each element. So let's figure out the grams of carbon. Well, if there are 92.26% carbon in my compound, that means that I have, for every 100 grams of the compound, I will have 92.26 grams of carbon. So that's why the 100 grams comes in easy, because this is a percent, right? It's 92.26 over 100. And if I assume 100, then that will cancel out, giving me exactly the amount in gram that is exactly the same as my percent composition. That's why we like to use 100 grams here. But the 92.26% tells me that out of 100 grams of compound, the compound, 92.26 grams are carbon. That's what that percentage tells me. So if I assume 100 grams of that, then the grams of carbon that I have would be 92.26. Now, if it gave me 1,000 grams, if the problem gave me 1,000 grams, then I would have 1,000 here, and I would have 922.6 grams carbon, right? Same thing. When I go to calculate the percent, the grams of hydrogen from the percent composition of hydrogen, I will take 7.743%. So that tells me that out of 100 grams of a compound, I have 7.743 grams of hydrogen multiplied by 100 grams. So they cancel out, leaving me with 7.743 grams hydrogen. So once again, if you assume 100 grams of the compound, then all you have to do is say, oh, I have 92.26 grams of carbon and 7.743 grams of hydrogen. And if you do the sum of these two, that gives you 100 grams of the compound, and you're good to go. The next step is to convert the amount of each element from grams to moles, and we do that by using their molar mass. If I have 92.26 grams of carbon, to convert this to moles, I use the molar mass of carbon. Make sure that you use the correct molar mass. You can't use the molar mass of carbon when you're dealing with hydrogen because they weigh differently. And start out with the amount that you're given, so 92.26 grams, multiplied by my conversion factor. 1 mole of carbon weighs 12.01 grams. My grams go to at the bottom because I'm converting to moles, and I want moles at the top. Grams will cancel, leaving me with 7.682 moles of carbon. I do the same thing with hydrogen. I take the mass in grams of hydrogen, 7.743 grams, multiplied by its molar mass, once again, and you can use a flow chart for this that I've given you in the previous video, where you start from grams and you want to get to moles and you use the molar mass and which form of that conversion factor you need, etc. So grams go at the bottom if I'm converting from grams to moles. My grams cancel, leaving me with moles at the top. And if I do the division, I get 7.682 moles of hydrogen. Now we can write the formula using these as subscripts, these numbers. So C 7.682, H 7.682. However, when we write empirical formulas or even molecular formulas, we need to use whole numbers. And for empirical formula, moreover, we use the smallest possible whole number ratio. So, first of all, these aren't whole numbers, and these aren't the smallest either. Well, what can I do to make them whole, and what can I do to make them the smallest whole number ratio? Well, I see which one of these is the smallest number. In this case, they're equal, so it doesn't matter. But we'll use another example where we have to figure out which of those three numbers will be the smallest, then divide everything by the smallest number. So in this case, since they're the same, I divide C 7.682 divided by 7.682, H 7.682 divided by 7.682. 7.682 divided by 7.682 gives me 1, and the same thing for hydrogen. So I get an empirical formula with a 1-to-1 mole ratio of C to H, which simply is written as CH. I don't write the 1 here because I divided both numbers by the same number. They're equal to each other. So it's the same as saying C1 to H1. It's a 1-to-1 ratio. This way, I have the smallest whole ratio, and it is a whole integer. So it's 1-to-1. I can't simplify that anymore because then I would get a non-integer. I would get a fraction, 1/2 or 1/3 or whatever. So 1-to-1 is the simplest whole number ratio for this compound. Now let's take a look at another example. Determine the empirical formula of a compound that has this mass percent composition. 37.51% is carbon, 2.52% is hydrogen, and 59.97 is oxygen. Once again, assume that you have 100 grams of a compound. Okay, so if I follow the example that I just did, 37.51 grams divided by 100 times 100 gives me 37.5 grams of carbon. If I do the same for the other two, I get 2.52 grams of hydrogen, 59.97 grams of oxygen. Now that I have the masses in grams, I need to convert these into moles, because when we write chemical formulas, whether they're empirical or molecular formulas, those are molar ratios, not gram ratios. So I have to convert the grams into moles by using the molar mass of carbon, the molar mass of hydrogen, and the molar mass of oxygen from the periodic table. This is what we've done here. So I took the mass in grams of carbon. I used the molar mass of carbon to convert to moles. Note that this is found underneath carbon in the periodic table. Use the flow chart if you have to until you get confident with how to set up the conversion factor. When I go from grams to moles, I divide by the molar mass. When I go from moles to grams, I multiply. And I do the same thing for hydrogen and oxygen. So dividing by the molar mass will give me 2.5 moles of hydrogen and 3.747 moles of oxygen. Now, I can write the empirical formula by using these moles. So for carbon, I have 3.123 moles. For hydrogen, I have 2.5 moles. And oxygen, I have 3.747 moles. Note that these are not whole numbers. And it's not the simplest whole number ratio either. So the first thing that we need to do is figure out which of these three numbers is the smallest. In this case, hydrogen subscript, or the moles of hydrogen, are the smallest. So I divide all three numbers, all three of them, by the smallest number, which is 2.5. So here's how I would write it. See, I take 3.123 moles of the carbon divided by 2.5. Hydrogen, 2.5 divided by 2.5, and oxygen, 3.747 divided by 2.5. Now the empirical formula gets a little more simplified to C 1.25, H1, and O 1.5. Note that this is still not a whole number ratio because these are not integers, they're still decimals. And how do I get these to be whole numbers? Well, if I multiply everything by 4, then I get a whole number ratio. So I take carbon, 1.25 times 4, hydrogen is 1 times 4, and oxygen is 1.5 times 4. This gives me 5. 1.25 times 4 gives me 5. 1 times 4 gives me 4, and 1.5 times 4 gives me 6. So the empirical formula then becomes C5H4O6. Note that I cannot reduce this any further because there is no common denominator of 5 and 4 and 6 of all three numbers that I can simplify them anymore by dividing through. If I didn't have the 5 here, if I didn't have the carbon, and if I had only H4O6, I could divide by 2, both the 4 and the 6 to simplify it further. But I can't because that 5 forbids me, because then it would become 5 halves, or it would be 2.5, which is not a whole number ratio. Okay, time for you to try your hand at one of these. So consider a compound with a mass percent composition of 53.31 carbon, 11.19 hydrogen, and 35.51 oxygen. Figure out what the empirical formula is for this compound, and assume 100 grams of that compound to make the math easier. Just follow the 2 examples that I already gave you.